Okay, so I'm going to show you how to use the Matlab toolbox, genetic algorithm toolbox, and the GA multi-objective optimization toolboxes, both to optimize, find the minimum of some of the test functions, basically. So for that, let's go to test functions, Wikipedia, and look at function that we can do. I believe you've seen how to do multi-objective, single objective functions, either with constraints or without constraints. Uh, these are all unconstrained problems. This group of functions are constraints. So the constraints are here. So all of these 5, 6, 7 functions are constrained, and you have solutions basically to compare. Let's pick one of these functions. It's like a more simple one, like this one. Single independent variable, just x. So Schaefer function number 2. So we could start by clearing this, and as I always recommend that you seed your random number generator to start this sort of an old / new random number generator. So if you run this, test. If you run this and you say rand, you'll get a sequence of random number generated same sequence. This helps tracks if you have errors or especially in heuristics, and if you have like some probabilities, like in PSO or ACO or just the regular genetic algorithms that you wrote. So with this, let's first write the function. We'll call it this output is equal to Schaefer function number 2, I believe, Schaefer number 2. And this takes in a value of x. And then if it's within the same driver file, you end it with end and not with return. So usually if this is like a 2-variable function, no matter how many objectives, so you'll say that x is equal all of the rows, the first column is equal to this is my x. So you take this big function or decision variables like the population, for example. It has many rows, so you take all the rows and the first column, which is x, and you'll say that this is y, this is x, and this is y. So this is all the rows, second column. So this way you can move between the x, the big X, and the y here, like here. For example, you have this function of x and y. You want to write it this way to make it easier on yourself. For now, we don't have anything, so just one variable, so we don't need this. Okay, so or to make it a small x, we'll retain this. What x will be if I type Schaefer number 2 and give it a value of like 3 or something, this will give me my x. So do this, it will give me 2. Let me write the function. Well, this is the output, and the output is a multi-objective function, so the output has 2 components. The first objective is given by just x, no, where is it? X squared. So instead of writing x squared, just in case this value x is a population of chromosomes, I'll write this dot before the caret so that it's applied element wise. So this is the first objective. and then output. The second objective is x minus 2 quantity squared. So this is x minus 2. I don't need a caret here. Then quantity squared. I need this, and then that's it. This is my function. If I do this and I evaluate it, it will give me first objective and second objective. So I want to use this function, and then the best way to do this is to look at the GA multi-objective Matlab, okay, and you'll hit the help page from MathWorks Multiobj, and this is the way it gives you the function. So you need the function handler, and you need to give it the number of variables, not the objectives, number of variables. This is the number of variables is the dimensions of the optimization problem. So number of decision variables in this case is 1. 2 objectives but 1 decision variables, and you can have linear inequalities, and then linear equalities, and then you can have lower bounds and upper bounds. This is unbounded if you use this format, and then you could have nonlinear constraints as we do now, and you could add options. So for now we just write GA completion, GA multi-obj. So GA, let's say x is equal to GA multi-obj of function handle is Schaefer number 2, and number of variables is 1, and I have nothing except, well, I didn't enter the constraints, so I have the constraints. That's not constraint. So that's it. So if I write this, GA multi-obj, GA multi-obj with a T. Okay. So it gives me the x, which is what? Which is x finds a local Pareto set. So if I say plot x, it will give me this line, but this is not a smart way to see the objective function of the Pareto surface. So what you want to do is plot. You could say in x and f val, so the value of the function x. If you run this, you'll have f val, which is the objectives, first objectives and second objectives. So if you say plot f val, again it doesn't mean anything, so because you're plotting 2 things. If you want to plot the first objective against the second objective, this way, it will give you a line. Again, we want to see like a Pareto surface, so I want to say, so let's make this using circles, and it will give you this. Okay. You can if you want a line, you have to sort them by their objectives. So you can have this. Suppress the output here and suppress the output here and run this, and it will give me this guy. So I'm gonna, okay, sorry about that. Okay, you can sort these. I'll say sort fval first according to the first objective, which is the first in fval, and this will give me sorted objectives. It will give me this sorted, but it will sort them without regard to the second objective. So I want the order. So I'll say that I want to get the sorted values, and then the location of these sorted values equaling this. So it will give me locations of element 1, tell me the 0 element is number 1, the second, this second one is almost 0, but not quite 0, is the 7th, and so on. So I want to plot, I don't want to plot fval against fval. What I want to do is I want to plot the sorted, which is fval according to 1, but fval 2, I don't want to have it in sequence 1 through L, but I want to have the locations. So if I do this, it will give me sorted. And if to prove to you sorted, I'll just say line. It will give me a line, and I can also remove the circles and make it like red or something. Okay, so let's look at another function. Let's say this is I want to see one of the functions that are optimized but constrained. So let's say we have which function? Oh, let's stick to this. You can have more options. Of course, you notice, and I got the results right away. Before I run, you can have many things. طبعا ما عندنا inequalities and equalities, the linear ones. We don't have them. We don't have bounds, or do we? We don't have we do have bounds. From minus a to a. So I can say in the bounds. Let's add bounds. Okay. So this is how many? So 1, 2, 3, 4, and then the upper and lower bounds. So this is 1, 2, 3, 4, and then the upper bound, let's say minus 1e5, and then the upper bound is 1e5, for example. If I do this, it will give me the same thing. Let's say blue with circles. Okay. One thing you can add is play with the options, because you see here you have nonlinear constraints. We don't have any constraints here. Okay? We'll try something with constraints in a bit. Now I want to add some options here, because it says options. So it discusses them one by one. So if I go to this one with options, I can see all the options I have, like function, display functions, and display Pareto option, Pareto surface plotting, and then Pareto fraction. So let's say that I want the options, the default options, opt set. So So this is the default so that you have something to work from, and then you add them one by one. So options مثلا let's say I want to set GA optim set of شنو ال quantity, let's say plot function plot شنو كانت plot function you can change it here. So plot function and you give it the value option plot function and then GA plot Pareto. So I'll say this is the option, and then I have to enclose it with curly braces. So GA plot Pareto. So I'll say GA at GA plot Pareto, and then I close the braces, and then I close this and do this. So I'll add this options. ما عندي nonlinear control, so I'll just say the options. And if I run this, it will give me the Pareto front. I'll see it being optimized. Okay. It will be done shortly. You could also set generation number, maximum generation, and the step. The set, the Pareto set size. We'll do that. Let's just let it finish. Let's stop. Can't stop. خلاص. Okay, let's say we don't want any of this. And we don't want any of this either. Actually, let's save it, and we'll in case we want to adjust something. So let's comment it out and say we want to try another function just out, which is the Kurosawa function. Kurosawa function. It has well, no constraints, but I'm gonna try it anyway because I want to show you how to write more complicated functions when you have more than one variable. So this is not x, but x, y, z. So the function is of x and y and z. So this is a chromosome, looks like this, xi, where I is from 1 to 3. So this is what you have, and the way to write it, Matlab البداية. So this is a function. I'll say the output is equal to Kurosawa, and it takes this x, and here I need to tell it exactly what I want. This is I goes from 1 to 3, so I might as well I'll say in the n var is equal to 3, so number of variables, and then I'll say in the number of objectives, because I'm looping over objectives. I don't need to loop over objectives, but n of is equal to 2, number of objectives, just to be complete. Okay, and then I want to say I want to add these output, this first objective and second objective. This is a sum. So I'll start by making them 0, and the way to do it is the output is equal to zeros. Zeros. I want rows, which is number of decision variables, and the columns is the objectives. So let's say this is the size of x, and let's use lower x بما أن ما كله 1x, so no need to split them. So this is size of x in the first dimension, because I need how many rows, and then an objective is the columns. This is what I have. This is nx, size of x. What's wrong with me? Zeros. Okay, so I'm initializing this all zeros, and objectives all zeros, and then I have to look for overall, let's call them chromosomes, equal to 1 through the size of x, but again in the first dimension. So number of objectives, number of decision variables, and within that for jj equals to 1 to the number of variables. Okay, and for each one, so I'll say in the output of this kk second objective, I have to compute the second objective first, and then because the second objective goes from 1 to 3, so I don't need to exit, and this I'll cut short. For output is equal to kk 2, I'll add output kk2, which is 0, I initialize to 0, plus the absolute value of x to 0.8. So this is absolute value of x kkjj, right? And then to the 0.8, and then plus 5 sine x to the third. So this is plus 5 times sine of x kkjj to the third, and close this and close one more, and that's it. So this is the thing, and I'll say y, our output function of x, y is a function of x, kk1, this is the first objective, is equal to the first objective kk1 plus minus 10 times the exponential of minus 0.2 square root, so this is minus 0.2 times square root of x squared. So this is x, this is x plus 1. So this goes 1, عشان كذي this does not go to 3, it will end. So this is x kk ii squared plus x kk I jj will I jj minus 1 or plus 1, and plus 1, all of this is squared, and we close this, square root and the exponential and the minus. So this I have this guy. But then I have but then this does not go to 3, so I cut it short after this. So I'll say if jj is equal to number of variables, so the last one don't count, so just continue, exit the for loop, and okay. Function out equals Kurosawa x n objective number of objective n obj equals 2. Okay, so let's try it. So let's say Kurosawa of let's say 1 2 3 3. Let's correct. We have 0s. Zeros 1 x size zeros. Okay, zeros size of x. Okay. The end functions. Okay, so it gives me something I want to minimize. Okay, so I'll see if there are limits. This function says that all of them go from -5 to +5, so I can add them me. I want this, so I'll say for this Kurosawa thing, I'll say lower bounds are equal to, for all of them, I can say 5 or -5, and it will take for all of them. If I don't specify them, if I don't put a 3 element vector, it will take for these values for all of the variables x, component x. So I'll just copy this. And I'll see what it gives me, not Schaefer, but Kurosawa function. This is -5. Let's say this is lower bound, this is upper bound, in case I don't need any options in me. So best number of variables is 3. Well, let's say this is n. Set everything here, n is equal to 3, and we'll run this, and it will give us optimization change. So this is the minimizer, and this is the function value. Again, I can do the same thing what I did here. Let me just copy what I did here, and ناحية options I'll just take these. So I'll copy these and say plot values. Okay. And this looks right because this way. Okay, you see that this doesn't exactly match this guy, right? This is nice and smooth. You have 1 point here. Okay, you have 1 point here, but still it doesn't it doesn't look nice. There are more than these options that we discussed. You can probably has something to do with the number of individuals or chromosomes in the first front. So that you can change. Also, you can specify the change the type of crossover or mutation, and then of course you can plot the Pareto surface and all the options they give you in the MATLAB. But I want to look at the options that are not given here in the we talked about plot Pareto في Pareto front option fraction Pareto fraction. Okay, this is set to by default to 0.35. So this is 0.35 of 35% of the population is located at the first front, the non-dominated solutions. So you could change this. Let's just get the option formula. This is guy, and we'll say option by default, and let's plot the function. And also we want another function, another option, which is function, not plot function, but Pareto fraction. Pareto fraction, and then I'll set it to let's say 0.5. And keep the same while plot. Let's look at plot function. Yeah, plot Pareto. Do this. Oh, I'm setting all the functions, but I didn't call the function, so I have to do this. Use the options. So it will plot this. You see, it has more individuals. I can also increase the population size, and I can also increase the way it terminates. So it terminates when it stalls. The GA stalls. So I don't know, 100 or 80 or 50 generations with no improvements, it cuts it short. Or when it reaches the function value tolerance, the function value minimum does not decrease by like 10 to the minus 5 for GA, or like 10 to the minus 4 for multi-objective GA, it cuts it short. So let's give it a moment, and let's compare what it's doing with this guy. This is minus 14 or minus 20 or 12. So 20, 12, 14, yeah, it's about right. Maybe they used anyway Matlab to come up with these. It's okay, it's done. You can again set the function tolerances. One of the things that is very useful is to tell it to new line. You just say max stall generations. Generations, yeah. You can change it to any positive integer, so this is the function tolerance, and you have to set them in tandem. It's better to set them in tandem, and so this is this guy also function tolerance, and we'll give it a value of x 1 minus 3 something. And then another option is the max stall generations, and you say, for example, I wanted to stop when it stalls for 150 generations, so it will continue solving. So that's it. Function tolerance function tolerance. Yeah. Function tolerance. Unrecognized parameters function tolerance. Options. E to the minus E. Okay. Function tolerance. No idea. Okay, it should work. It's very important. Okay, forget this. Fine. Still have a stop. Okay, it stopped. Let's try, lastly, try function with the constraints. I want this. Let's try something with constraints. Well, this is getting to be a long video. ولكن let's look at a simple function with constraints. Let's look at the first one here, in and con. So this is a two objective function. We'll just change this. So function in con, it takes value x, and the output is assigned, and then end function, and function is you can split them. Or you can leave them as we can do this x thing you normally do. ولكن let's say, let's keep them as is. So this is a function of output. This is the first objective and the second objective. So you want to put them in columns. Okay, so this is the first, rows. This is the first row, this is the second row. This is how Matlab understands it. So the first row is 4 times x squared minus x squared. So this is output is equal to 4. And I'll use this just in case I'll use this function later for a GA or a multi-objective GA that I write. So I'll do this, and this is x, all of the chromosomes of the values, x, so the first column, and then dot raised to a power 2 plus 4 again dot times x and y. So this is all of it, and then the second column again dot raised to the power 2, and I'm done with my first objective. So I'll start a second row, and I'll say that This is x minus 5, y minus 5, quantities squared. So this is x x1 quantity squared, so minus 5 rather. So minus 5, I don't need a dot for a minus 5, so quantity squared plus same thing, this one squared minus 5. Okay, and I'll close this, plus. I need yeah, and I'll suppress the output. So this is my output, and that's it. End. However, I need to also write the constraints. I have limits in so I'll remember to change the limits. So the constraints, I'll give them as the same function name, constraints. So so end here. So the constraints, I have more than one constraint. So but they're all inequality constraints. So no equality constraints, no linear constraints as many of the examples, but I have have two nonlinear inequality constraints. So when I say here CEQ, this is the nonlinear constraints given by this nonlinear constraints given by these. I have a couple of these and none of the equality nonlinear constraints. So this tells me in the way Matlab understands it is when you have nonlinear constraints, they have to have a less than or equal to 0, each one of them. Okay, and these equality constraints less than or equal 0. So when I have these constraints, I have to say less than or equal to 0, and this I have to transform. So -1 here, -1 here, and then I'll take to the other side. So let's enter these. So this is x minus 5 quantity squared plus y. So this is the output, not output anymore, but this is C and CEQ. This is how Matlab wants it to be. So first CEQ is equal to nothing, and C is equal to, again, I have two of them. So the first one, the first row, just I wrote this here, is quantity squared. So I'll open a bracket, and then x, I can split them into x and y. That's in the I know the idea. So this is all of the chromosomes, just in case. It doesn't need to be here. And then -5 quantity squared plus 4 plus y squared. So this is plus x, all of it, second column, quantity squared, and then I have to move this to this side. So this is -25, and this quantity will be less than or equal to 0. Okay, so I'm done with my first constraint. My second constraint, let's make sure, okay. My second constraint is I have to multiply both sides by -1 and bring this over, or just take this to the other side, so that quantity here is less than or equal to 0. So either way. So I'm gonna enter these. Well, I'll add a minus sign here. So this is minus x, but then y, so this is x, all of it, first column, which is the x, minus 8, quantity squared, minus in x y, so all of the chromosomes, minus plus 3, so plus 3, actually I need هذا, so that when I say quantity squared, I'm catching all of it, y will y and the 3, so this is quantity squared. This is for the first one. I need to I added the minus here and the minus here, so this is minus and this is minus, so this is the first minus, this is the first minus, and then this will be flipped and this will be minus, but it will go to the left hand side, it will be plus again, so this is plus 7.7. Got it. So I'll end this. So these are my nonlinear constraints. Now when I say let's copy of this and comment it out and say that this is thin and corn. Is it corn? Yeah. So number of objective is 2. What number of variables is 2, the x and y. So I can just enter them directly. I don't need this. I don't need this. I don't need all of this. So number of objectives, this is then continue, then core, like it, function, and then I have at then at corn underscore constraint const. Yeah. Okay. Options. Yeah, why not? Let's activate them again. And no linear equality or inequality constraints. So no AEQ or BEQ, ولا inequality constraints. Lower bounds and upper bounds. This is lower bounds on zeros, and then 5 and 3. So lower bound, this is 0, 0, and or you could enter the cases 5 and 3, and number of variables. 2, and then that's everything. So I'll run this unbalanced parentheses, and this is my x. This is the function constraints. So this is the first constraint, squared my or plus. So this is constrained. X after 5. Yeah. So run this and it will churn on. Okay, so this is 100. This is a Pareto surface. This is 105. So let's look at the function. This is 105. Looks 105, but this is spread more than our solution. So let's look at this. This is 140. Okay, so this is 105. Okay, that looks good. So you can play around and increase the number of individuals in the first front, and that's it basically. I'll stop here and wish you good luck. Done. Okay, so this is crooked. Listen, you can play with the population size, the crossover type, which is it makes a huge difference Okay, the crossover type, it makes a huge difference. The most common like the crossover option that you could do is intermediate value crossover. You can specify all of these options in the option here, and you can run it طبعا بالماتلاب. So let's stop here and